Welcome to Factory on Air by DBR77, where smart manufacturing gets real. This is episode 18, Eliminating the 7 Wastes of Lean with Simulation. Lean tells us to cut waste. But in practice, identifying overproduction, waiting, and inefficiencies isn't easy. In this episode, we explore how simulations and real-time data can make the 7 wastes visible, measurable, and removable. You'll learn how digital twins, process modeling, and AI help you spot delays, excess motion, and hidden bottlenecks before they become costs. We'll show how DBR77 supports Lean not just as a philosophy, but as a daily, data-driven practice. Factory on Air is powered by DBR77, the platform that brings Lean principles to life with simulation, analytics, and smart decision-making. Let's get into it.
Welcome back to The Deep Dive. Today, we're really focusing on something critical for anyone deep in operations, especially, in competitive manufacturing.
That's right.
We're tackling a core concept, lean manufacturing, but specifically, the really tough part, finding and, crucially, getting rid of those 7 types of waste, the MUDA.
Yeah, it's foundational, isn't it?
Yeah.
Lean's been around forever, it feels like, but the truth is, in today's factories, they're complex, high mix, high volume. These wastes, they aren't just lying around in plain sight.
No, they're hidden.
Exactly. They're insidious. They hide in the process gaps. They hide in demand fluctuations. Sometimes they're just baked into how things have always been done. Inertia,
Absolutely. And the old ways of finding them, the clipboard, the stopwatch, walking the floor, they might spot a symptom, maybe a bottleneck here or there.
Sure, sometimes.
But they rarely get to that deep systemic root cause you need for a permanent fix. So here's the thing. If Lean is all about efficiency, all about optimization, why are factories still struggling to see exactly where the money's leaking out?
That is the million-dollar question, isn't it?
Yeah.
And it's exactly what our source material digs into today. We're going deep on how modern tech, specifically simulation and advanced data analysis, takes these abstract hidden losses and makes them, crystal clear targets.
Targets you can actually hit.
Precisely. We're moving past the guesswork, past intuition, and really into the realm of, let's call it, digital certainty.
Okay, let's unpack this then. Our mission today is to really understand how technology gives us that visibility, that analytical muscle, to truly conquer the 7 wastes. Right, first things first, we need a solid foundation. We have to start with those 7 categories of waste, MUDA. Basically, any activity that eats up resources but doesn't add any value for the person actually buying the product.
Got to know your enemy.
Exactly, step 1.
That's right. And the whole point of Lean is to systematically find and, crucially, permanently get rid of all 7. It's a powerful framework because it touches everything: supply, movement, quality, time, the whole system.
Okay, so let's define them. Maybe as we go through each one, we can touch on why they're often so hard to spot just by looking.
Good idea. Let's start with probably the most dangerous one because it causes so many downstream problems. Overproduction.
Oh.
This is simply making more stuff than is needed right now, or making it too fast, too early. When you overproduce, you instantly create other issues.
Like what?
Well, you suddenly need extra space to store it. Right? That's inventory waste. You need extra transport to move it. You've tied up capital in things just sitting there, not sold yet. It's like knocking over the first domino.
Boom, boom, boom. Okay, that makes sense. And that leads right into the second one, which I guess you can see if it's really bad, but it can be subtle too. Waiting.
Waiting. Dead time. It's material sitting between steps, waiting for a machine. It's an operator standing around waiting for parts to show up. Or maybe a machine just sitting idle, waiting for maintenance or setup.
Any time value isn't being added, basically.
Exactly. But your capital, your resources, they're still tied up. It's pure waste.
Next up.
Transport. Now, this is about moving materials, parts, finished goods around the facility inefficiently, unnecessarily, excessively.
So moving stuff isn't adding value.
Not unless it's the final truck heading to the customer, no. Movement inside the plant just adds cost, it increases the risk of damage, maybe things get lost, and it definitely burns time. The problem is internal logistics often just sort of evolve organically.
Right. Nobody necessarily planned that crazy route for the forklift.
Precisely. So it becomes almost impossible for a person just watching to visualize the truly optimal flow.
Okay, following transport, overprocessing, This one feels a bit sneaky.
It is subtle, yeah, because often it comes from a good place, like trying too hard on quality.
Doing more work than the customer actually asked for or needs.
Exactly. Maybe using a super high precision machine when a simpler one would do, or doing 2 quality checks when the specs only need 1 and the process is stable anyway. It's wasting resources, time, energy, machine capacity on work that doesn't add value in the customer's eyes.
Got it. Number 5.
Inventory. This is the physical stuff, the raw materials, the work in progress or WIP, and the finished goods that represents tied up capital. Excess stock.
An inventory isn't just about the cost of storing it, right?
Definitely not. That's just the tip of the iceberg. The real danger of excess inventory is that it hides other problems. If you've got massive buffers of parts everywhere.
You don't feel a pain when a machine breaks down or a supplier is late.
Exactly. The underlying problem, the machine instability, the unreliable supplier, it gets masked by the inventory cushion. So it never gets fixed. It persists.
Okay, that's a key point. Now, help me clarify the difference between transport, which we talked about, and number 6, motion.
Good distinction. Transport is about materials moving longer distances between areas or workstations. Motion is about inefficient movement at the workstation. It's the operator twisting awkwardly, bending down unnecessarily, maybe walking 3 steps to grab a tool or flip a switch, searching for something.
Little things.
Seemingly little things, yes. But add them up over an entire shift, hundreds of times a day. It becomes massive lost time. Plus, it contributes to operator fatigue and even potential injuries.
Right. And the final one, number 7.
Defects. This one's pretty straightforward. It's the rework, the scrap, the errors, anything that isn't made right the first time.
The most obvious loss, maybe?
Often, yes. It directly consumes resources, more labor, more materials, more machine time, just to fix the mistake. And that often causes delays, maybe missed shipments, unhappy customers. It compounds.
Okay, so we have our 7. Overproduction, waiting, transport, overprocessing, inventory, motion, and defects. And like you said, the trick isn't just knowing the list.
No, not a...
It's finding them when they're all tangled up together or when fixing one thing, like adding inventory to stop waiting, just makes another waste worse somewhere else.
Exactly. That's the systemic challenge. And that systemic challenge is precisely where modern tech makes the difference. You know, for decades, spotting these wastes relied on someone watching, maybe timing things for a bit. Subjective observation, limited data.
Yeah, if you've got, say, 1,000 different part numbers running across 20 machines, how on earth do you track every single unit's wait time or every operator's little movements?
You can't. It's humanly impossible at that scale and complexity.
Right. You might know your overall equipment effectiveness, your OEE, is maybe 60%. But can you easily prove if that missing 40% is because schedules are messed up, causing waiting? Or is it lots of tiny stops and fixes, which is motion or defects? Or maybe your suppliers are just dumping too much raw material on you. Overproduction leading to inventory.
You're guessing. And this is exactly why simulation has become, well, almost an imperative. Simulation lets you create a precise representation, a digital copy of your real production and logistics processes.
So you build the factory.
Right.
Virtually.
Exactly. You build a virtual model of the plant, its machines, its specific operating rules, even the operators and their tasks, a high-fidelity environment.
And when you hit play on that digital model, what's the key thing you suddenly see that was invisible before?
You get what our sources call the visualization of waste in motion. You can literally track every single part, every forklift journey, every operator action, but you can do it over a simulated timeline. You can simulate weeks, months, even years of operation in just minutes or hours.
And this visualization, it's not just numbers on a spreadsheet, is it?
Oh, far from it. We're talking dynamic, often visual spatial analysis. For identifying waiting, for instance, the simulation can generate heat maps. They literally show you where queues of parts or materials pile up most often, and critically, how long they sit there festering.
Okay, I can picture that.
For transport and motion, it can automatically create what are called spaghetti diagrams. Imagine tracing every path taken by a forklift or an operator over a shift.
A tangled mess, probably.
Often, yes. The simulation draws those actual complex crisscrossing routes, instantly highlighting unnecessary travel, backtracking, wasted miles. And for overprocessing, you can see the impact of, say, an extra inspection step on the overall cycle, time, and throughput. Does it actually improve quality enough to justify the delay?
So it makes the waste visible in space and time. But here's a question I hear sometimes. Lean principles date back to, the 1950s. Why do we suddenly need this complex digital twin tech to find these seemingly basic wastes? Isn't this just a fancy way to fix bad management?
That's a fair question, and it gets to the heart of it. The answer is the sheer complexity of modern manufacturing. It's not necessarily bad management, it's the scale, the dynamism. Factories today rarely just make one thing smoothly. They juggle hundreds of product variations, constantly shifting schedules, custom orders, unpredictable supply chains.
Right, it's chaotic.
It can be.
Mm-hmm.
And in that dynamic, high variability environment, traditional static lean analysis it breaks down. It can't keep up. The digital twin provides the analytical horsepower needed to handle that complexity and uncertainty all at once.
So the complexity justifies the tool. And that tool, this virtual model you use to monitor, optimize, test things out, that's the digital twin, right?
That's the concept, yes.
Yeah.
A living virtual replica.
And what's the absolute killer feature of this digital twin when you're fighting waste?
Without a doubt, it's risk-free testing. This is the absolute game changer. Once the simulation helps you pinpoint, say, those tangled transport routes.
The spaghetti diagram mess.
Exactly. You can then test potential fixes virtually. Maybe you simulate moving a storage area or changing the physical layout or altering the sequence of operations, maybe even adjusting staffing levels. You try it all out in the digital world first.
So you can say, okay, if we move this machine here, simulation predicts it will cut wait time by 18% before you actually shut down the line and call the riggers.
Precisely. You get a highly confident prediction of the outcome before you spend a dime on implementation, before you disrupt production, before you potentially make things worse.
Yeah. Because you could test a layout change that fixes transport, but then discover, whoops, it creates a huge bottleneck somewhere else, making waiting and inventory skyrocket.
And if the simulation shows that, you just discard that idea. No harm done. You try another scenario. The digital twin is the ultimate virtual laboratory for finding the best way to minimize all 7 wastes together.
Okay, this simulation, this digital twin, sounds incredibly powerful. But there's that old saying, right? Garbage in, garbage out.
Absolutely fundamental. Our sources really hammer this point home. The simulation is only ever as good, as reliable as the data feeding it. Without accurate, timely, granular data, that fancy digital twin is just, well, an extensive animation.
Right. It won't reflect reality.
Exactly. Data is the fuel. It's what turns a theoretical model into practical, actionable, quantifiable insight. And we need specific types of data streams to really zero in on the 7 wastes effectively.
Yeah.
Aggregate data, summary data, it just won't cut it. The sneaky wastes, the microstops, they stay hidden.
Okay, let's break down those data needs. What about the core operations? What data points are crucial for spotting things like defects and waiting?
You need deep operational data. We're talking cycle times measured accurately, maybe down to the second. You need the precise start and end times of any machine downtime or stoppages, and critically, the reason for the stop.
Not just machine 3 was down for 30 minutes today.
No, that's useless for root cause analysis. You need to know when it stopped, why it stopped, was it a breakdown, a tool change, waiting for material, and how often that specific reason occurs. If a machine hiccups for 2 minutes every hour because of a minor alignment issue,
that's 16 minutes lost per shift. That adds up.
It absolutely does. That could be classified as waiting, if it's waiting for adjustment, or even defects, if the misalignment causes bad parts. The system needs to capture that granularity to spot the pattern and let you fix the real cause.
Okay, operational data is key. What about the waste related to movement, transport, inventory, and that root cause, overproduction?
For those, you need detailed logistical data. This means tracking material movement, where did it come from, where did it go, when, exact timestamps for transfers between workstations or storage areas. You need real-time inventory levels, not just in the main warehouse, but also at all those little buffer zones on the floor, the WIP inventory.
The stuff that hides the problems.
Precisely. And you need data on supplier deliveries, lead times, quantities. All this logistical data helps expose inefficient routes, transport, confirms if your stock levels, inventory, are truly necessary or just bloating from poor planning over production, and highlights issues like suppliers.
What's really interesting here is how having all this dense, real-time data allows for a different kind of analysis, right? It's more than just looking back.
That's the strategic shift. That's where the real competitive advantage kicks in. We move from just reactive analysis to something more like prescriptive strategy. Most places operate on historical analysis. They look at reports. Here's what went wrong last week or last month.
All right.
But when you feed that continuous stream of granular, operational, and logistical data into the digital twin, you unlock predictive analysis.
Okay, so instead of just saying, yeah, we had 10 breakdowns on line 5 last week, what does the predictive layer tell you?
It allows you to forecast potential problems before they happen. The system might calculate something like, okay, based on the current production rate, the variability we're seeing in component Z deliveries, and the current WIP levels, there's a, let's say, 75% probability that Workstation 7 is going to become a bottleneck by 2 p.m. tomorrow. This will likely cause a 3-hour queue if the current schedule isn't adjusted.
Wow, so you could actually step in and prevent that waiting time from ever occurring.
That's the power. You can intervene proactively, adjust the schedule, maybe reroute some flow, talk to the supplier. You solve the potential problem before it hits the floor. This is how you make improvements stick. You stop constantly fighting fires and start preventing them systemically.
Okay, theory and potential are great, but results talk. When we talk about finding invisible waste, people need concrete proof that this simulation approach actually delivers big returns. Our sources had some really impressive examples.
Yeah, these case studies are fantastic because they show how tackling seemingly small local inefficiencies with simulation can lead to massive overall gains. Let's start with that one focused on the most granular waste. Motion.
Right, the electronics producer. What's interesting here is they didn't go buy fancy new robots or anything, did they? They focused purely on the human operator's workflow.
Exactly. They built a detailed simulation model of the operator's movements right there at the workstation. Every reach, every turn, every step. And the simulation immediately flagged these specific, repetitive, unnecessary movements. Stuff like walking 2 extra steps back and forth between assembling part A and grabbing the tool for part B hundreds of times a shift.
Things you'd never notice just casually watching.
Probably not, or
Yeah.
you dismiss it as minor. But by simulating it, they saw the accumulated waste. So they redesigned the work cell layout slightly, moved tools closer, changed the sequence a bit, just eliminated that wasted motion.
And the result? Just from optimizing those movements.
A 20% increase in that workstation's efficiency.
20%.
Just from optimizing the physical workflow based on simulation insights. That's a huge productivity jump, achieved by making better use of their existing people and space. Classic lean, amplified by technology. No big capital spend.
Wow, that 20% could easily be the difference between profit and loss on a product line.
Okay.
Okay, next example tackling a big logistical waste. Overproduction.
Yes, the food plant example. This one's compelling because food production often deals with tricky, fluctuating consumer demand. They use detailed demand data fed by their actual operational data into their simulation model.
So they weren't just guessing demand and making huge batches just in case.
Exactly. They moved away from that safety net of constant overproduction. They simulated different production schedules based on forecast scenarios, trying to sync up production much more tightly with actual predicted need.
Okay, so they stopped making stuff that might just sit there and potentially spoil.
Precisely. By tackling that fundamental waste of overproduction, the direct result was cutting their storage losses waste tied up in inventory and potential spoilage by a massive 30%. And think of the ripple effects. Less need for expensive cold storage, less capital tied up in stock, fresher products for the consumer. It's a win-win-win.
30% is significant. Okay, finally, the automotive example. This one tackles transport. And changing the layout in a huge car factory, that sounds like a monumental, maybe even prohibitive task.
Which is exactly why simulation is indispensable for this kind of problem. The automotive factory didn't start by moving heavy equipment around. No way. They built a digital twin of their entire production hall layout.
The whole thing.
The whole thing, including all the internal transport routes, the automated guided vehicles, AGVs, the delivery points, everything. Then they simulated thousands upon thousands of material movements through that virtual layout.
And what did the simulation show them that they couldn't see just by looking at the floor plan or watching the forklifts?
It revealed incredible amounts of redundancy and unnecessary travel. Massive backtracking. Parts being moved clear across the hall, only to end up back near where they started later on for a subassembly. Just inefficient routes galore.
So what did they do?
Based on the simulation results, they optimized the locations of staging areas, rerouted the internal delivery paths, and changed material flow sequences, all tested virtually first. The simulation proved they could eliminate an absolutely staggering 80% of the unnecessary internal transport movements.
80%. That's not tweaking. That's a fundamental re-engineering of their internal logistics.
It absolutely is. And think of the savings: less fuel or battery consumption for transport vehicles, less wear and tear, reduced labor for driving, faster material delivery to the lines, less risk of damage during transit. It's enormous.
These examples really drive it home. The biggest wins seem to come from fixing wastes that were either too small and repetitive to notice easily, like motion,
Or too complex and system-wide to analyze properly, without a powerful tool, like transport and overproduction in these cases. Wastes that were just accepted as the cost of doing business.
Until simulation made them visible and solvable. Okay, achieving something like an 80% reduction in transport. That takes more than just one piece of software, right? It sounds like you need a whole connected system, an ecosystem.
That's exactly right. It has to be a systemic framework that links the data, the modeling, the prediction, and the decision-making intelligently.
How do organizations actually put that ecosystem together? How do they tie all these pieces, simulation, data, decisions, into something that works systemically?
Well, the key is it needs to be holistic and iterative. It's designed from the ground up to map, identify, analyze, and test fixes for all 7 lean wastes, ideally within one integrated digital model, not just looking at one waste in isolation.
Okay, walk me through the core components of this system.
It really starts with modeling and data integration. Step 1 is building that comprehensive digital twin of the plant, the processes, the logic, making sure the model accurately reflects reality. This model becomes the central hub, the brain, for all the waste analysis.
And how does this brain get its information, its constant stream of accurate data?
That's the nervous system. IoT solutions, the Internet of Things. You need sensors, connected devices, maybe RFID tags, gathering data instantly and continuously from everywhere that matters. Machines, PLCs, maybe operator input terminals like MES stations, warehouse systems.
Real-time data flow.
Crucial. Because IoT provides that super granular real-time data you need for accurate simulation, and especially for that predictive analysis we talked about. It also dramatically cuts down the time and effort compared to someone manually logging data.
Okay, so you've got this torrent of real-time data flowing into the digital twin brain. Now, how does the system automatically detect the 7 wastes within that data?
It uses sophisticated algorithms for automated detection, often tailored to each waste type. For weighting, for example, it might correlate GPS or RFID location data of materials with the status data from machines automatically flagging units that are sitting idle for too long between processes.
Okay.
To spot overprocessing, it can compare the actual steps recorded for a part against its standard-defined process route in the system, highlighting any extra unplanned operations or checks. For transport, it analyzes those movement paths we discussed. For defects, it tracks quality data, pinpointing where errors occur most frequently and even trying to correlate them with upstream process variations.
So the system flags potential waste areas, but just knowing waste exists isn't enough. How does it help figure out the best way to fix it, especially when a fix might affect multiple things?
This is where it gets really advanced, moving into AI for action. Artificial intelligence, often machine learning, takes it to the next level. It doesn't just suggest a fix. It uses the predictive power of the digital twin to test hundreds or thousands of potential scenarios automatically.
So the AI simulates the ripple effects of a proposed change.
Exactly. It models the cause and effect. If we propose reducing inventory levels for part X by 15%, the AI uses the simulation to predict the likely impact on, say, potential machine waiting times downstream, or maybe on the transport frequency needed.
It gives you a data-driven risk assessment for every option before you touch anything in the real world.
Precisely. The system recommends the most promising streamlining actions based on simulated outcomes. It quantifies the expected benefit cost savings, time reduction, and crucially, simulates the impact across all 7 wastes before implementation. This helps avoid those unintended consequences where you fix one leak only to spring 2 bigger ones elsewhere.
Now, beyond the simulation software and the IoT sensors on the floor, our surveys also mention a more strategic layer needed for management. Something about ensuring these tech investments actually align with business goals.
Yes, that's absolutely critical. A common failure point for these big digital transformation projects is implementing tech in silos, without a clear strategy connecting it back to the overall business objectives. That's where methodology like the Digital Development Roadmap, DRD, mentioned in the sources, comes in.
Okay, what does this DRD actually do?
Think of it as a structured maturity assessment. It helps management evaluate where the company currently stands digitally across a whole range of areas the sources mentioned over 27 operational, development, and tech dimensions. It's basically strategic health check and gap analysis for digital capabilities.
And how does knowing your digital maturity help eliminate waste on the factory floor?
It ensures alignment and prevents wasted investment. By understanding the company's current state and digital readiness, the DRD helps make sure that any new initiatives, like investing in a sophisticated digital twin platform, directly support the main business goals. It stops companies from making the mistake of buying isolated point solutions, one piece of optimization software for just one machine line, when what they really need is a systemic, integrated approach to tackle all 7 interconnected wastes across the whole value stream.
So it guides the investment towards a holistic solution.
Right. It helps prioritize. It lets management see their progress on the digital journey and make informed decisions about the next steps that will deliver the biggest bang for the buck in terms of waste reduction and overall efficiency.
Okay, we've painted a picture of some incredible potential here. We're talking 20%, 30%, even that staggering 80% improvement in the automotive case, often without buying major new machines. But, if this technology-enhanced lean is so powerful, why isn't every single factory already transformed?
The reality check. The technology works, the potential is absolutely there, but the path to actually implementing it and getting those results, well, it runs straight into some very real organizational and human hurdles. But first, maybe let's just quickly reinforce why companies pursue this. What are the big picture benefits?
Good point. Beyond just cutting waste percentages, what's the overall impact?
It's pretty comprehensive. First off, you see tangible, lower operational costs. Less waste means using fewer resources, materials, energy, labor hours per unit. That flows right to the bottom line. Second, because you stabilize and optimize processes before implementing changes, you generally achieve higher product quality with fewer defects, less scrap, less rework.
Right, hitting that defects waste hard.
Exactly. And then what about the customer? How do they benefit?
Good question. Does it make a difference to them?
Absolutely. When you eliminate all those internal delays, the waiting, the unnecessary transport, your overall production throughput naturally speeds up. So customers experience shorter order fulfillment times and much better on-time delivery. Reliability goes way up.
And internally, what about the people working there?
This is a big one. When you give operators access to objective data, maybe through dashboards tied to the system, and you empower them to suggest improvements that can then be simulated and tested, you foster increased employee engagement. They become active participants in improving their own work environment. And ultimately, this helps build the most valuable thing, a sustainable culture of continuous improvement.
Okay, that all sounds fantastic, the ideal state. But as you said, transforming a culture, especially one that might be decades old, isn't easy. What are the main roadblocks, the implementation challenges?
The first one, often the biggest technical headache, is simply lack of data or data scattered everywhere. Many companies have the data, but it's locked up in different silos. The MES system here, the ERP over there, maybe a separate warehouse management system.
Getting it all talking to each other and feeding the digital twin cleanly is hard.
It can be incredibly complex and time-consuming. And if you can't measure it accurately and consistently, you can't simulate it reliably. That's hurdle number one.
And then there's the human element, that we've always done it this way mentality.
Oh yeah, organizational resistance to change. It's huge. You might have a supervisor who's run their department successfully for 20 years based on experience and gut feel. Now a computer system tells them that 20% of their team's movement is wasted. There's natural skepticism, maybe even fear.
Fear of being replaced or just distrust of the black box.
Both,
Yeah.
potentially. The system has to be presented and used as a tool to enhance their expertise and decision-making, not to replace them. Which leads to another challenge. The difficulty visualizing abstract losses, especially for managers who aren't deep in the technical weeds.
How so?
Well, telling an executive you're losing $50,000 a month in excess inventory carrying costs might get a nod. But showing them a simulation heat map where massive amounts of virtual cash are just sitting idle in buffer zones, that hits differently. They need to see the waste in the process flow, not just on a spreadsheet, to really feel the urgency.
So bridging that gap requires education.
Absolutely critical. There's a profound need for organization-wide education. It has to reach everyone. From the operators on the floor, who need to understand why the data they input or generate is important, all the way up to senior management, who need to champion the initiative and make the strategic investments.
If only the engineers understand the digital twin, it's doomed.
Pretty much. It won't get the buy-in or the sustained effort needed. Everyone needs to understand the why and their role in it.
Yeah.
Otherwise, you risk falling back into that trap of implementing isolated, disconnected point solutions that don't address the systemic nature of the 7 wastes.
Okay, we've covered the why, the what, the how, the benefits, and the barriers. Let's bring it all together with some practical steps. For someone listening who's thinking, okay, I want to take this systemic, data-driven approach, what's the playbook derived from our sources?
Right. This is the roadmap. The 7 practical steps for waste elimination using simulation, framed within that continuous improvement mindset.
Step 1 sounds logical, but it's key for focus. Identify processes likely containing waste. You don't boil the ocean, right? You start somewhere specific.
Exactly. Don't try to model the entire factory on day one. Pick an area that's a known bottleneck or a process with high variability, lots of complaints, maybe high scrap rates. Start where the pain is likely greatest.
Step 2, collect data. Get the fuel for the fire.
Yes, this is where that IoT infrastructure becomes so important. Gather that accurate, real-time, granular data from the machines, the warehouse, the workstations in that chosen process area. Remember, garbage in, garbage out. Accuracy is paramount if you want the model to be trusted.
Step 3, create a digital twin, or at least a simplified process model. Build your virtual sandbox.
Model that process segment. Get the timings right, the logic, the constraints. Build a virtual representation.
Step 4, identify visible wastes using the model.
Now you run the simulation. Let the software do its work. Generate those heat maps for weighting, the spaghetti diagrams for transport and motion, analyze the cycle times for overprocessing, track the defect propagation, pinpoint where in the virtual process the 7 wastes are actually occurring.
Okay, you found the waste. Step 5, simulate changes. This is the magic part.
This is where you experiment risk-free. Test different layout ideas. Try changing the work organization, maybe the batch sizes, the scheduling rules. Run dozens, maybe hundreds of what-if scenarios. See which changes actually reduce the targeted waste without causing problems elsewhere.
Step 6, select the best variant and implement it in reality.
Based on the simulation results, you pick the change or combination of changes that gives the best overall improvement, and you implement it on the actual factory floor with high confidence, because you've essentially pre-validated its effectiveness virtually. The risk is dramatically lower.
And finally, step 7, which makes it sustainable. Measure effects and continue improvement. Close the loop.
Absolutely. The data collection doesn't stop. You monitor the real-world impact of the change you just made. Did it deliver the predicted results? Feed that new performance data back into the digital twin. Maybe it reveals the next bottleneck, the next opportunity. It becomes a continuous cycle of refinement.
So if we wrap up with the bottom line impact on efficiency, what's the key takeaway?
The key takeaway is powerful. Using these advanced tools, simulation, digital twins, AI, to systematically eliminate the 7 lean wastes is very often the fastest and most capital-efficient way to significantly boost efficiency.
Faster than buying new machines.
In many cases, yes. You avoid the huge capital expenditure, the long lead times, the installation disruption associated with major equipment purchases. Instead, you focus on maximizing the productivity, the throughput, the profitability of the assets you already have.
So it's about blending that classic lean philosophy, the relentless focus on waste elimination, with the incredible analytical power of modern technology.
Precisely. That combination creates an incredibly potent tool for building and sustaining competitive advantage. It leads directly to higher productivity, faster cycle times, better resource utilization across the entire operation. #tag outro.
Well, that brings us to the end of another deep dive. I think the core insight we've really unpacked today is that mastering lean in the modern era isn't just about memorizing the 7 wastes anymore. It's about having the digital visibility, that high-fidelity digital twin, to see exactly where waste originates and to rigorously test ways to eliminate it. Simulation makes the invisible visible, the abstract concrete.
Couldn't agree more. And it's important to remember, the underlying principles here using data, modeling complexity, simulating solutions to stop guessing they apply far beyond the factory floor. You can use this thinking to optimize almost any complex process, whether it's in manufacturing, logistics, healthcare, even administrative workflows. It's about leveraging data for proactive, systemic improvement.
So here's a final thought for you, our listener, to chew on as we wrap up. We heard that automotive factory example where they cut unnecessary internal transport by a massive 80% just by simulating their physical layout. If that much physical inefficiency could hide in plain sight, what percentage of unnecessary digital movement or waste might be hiding in your own organization's processes right now?
Yeah, think about things like redundant data storage consuming cloud resources, excessive processing cycles, inefficient data transfers between systems. How much digital muda is currently invisible and costing you money or time?
Something to mull over. The principles of waste minimization definitely extend into the digital realm, too.
Indeed they do.
Thanks for joining us for this deep dive. We'll catch you next time.